So thank you all for coming today. I want to welcome you to our first PRISM seminar of the spring semester. I believe we have a great one today, so I hope you do as well. And hopefully everyone's doing as best they can given state of the world. Um, Today we have with us Dr. Alfonso J. Martinez. Dr. Alfonso J. Martinez is an assistant professor of psychometrics and quantitative psychology at Fordham University. He obtained his BA in psychology from California State University, Fresno in 2019, an MA in psychological and quantitative foundations, and an MS in statistics, and a PhD in psychological and quantitative foundations from the University of Iowa in 22, 23, and 24, respectively. His research focuses on the development, evaluation, and application of novel psychometric, statistical, and computational methods for the social, behavioral, and psychological sciences. His areas of expertise are in generalized latent variable and psychometric modeling, Bayesian inference, measurement invariance, probabilistic graphical models, mixture modeling, and statistical algorithm development. His methodological research has been published and featured in quantitative methods journals such as Psych, Multivariate Behavioral Research, and British Journal of Mathematical and Statistical Psychology. So join me in welcoming Dr. Martinez here, and thank you.
Yes, thank you. Thank you, Clint. I'll start sharing my screen here. Okay, so hopefully that is working as expected. Looks good. Okay, thank you. Okay, yes, thank you. Thank you, Clint, for that really great introduction. And also thank you to Susanna, Daphne, and the rest of the PRISM group for organizing this event. And thank you to all of you who are here in attendance now, and those who will watch later in the future. It's a real great honor to be here, and I'm really excited to be sharing some recent work I've done on trying to answer this question of building adaptive assessments for psychological assessments with continuous response formats. And I want to start by just briefly going over the traditional measurement assessment paradigm that is very common across several different domains. This traditional assessment paradigm is usually we are trying to say some sort of statement about a person with respect to some latent construct that we're interested in. And to do so, we develop assessments that tap into that latent construct that we're interested in. And usually the way this traditional paradigm, this assessment paradigm operates is we have a group of individuals, respondents or examinees in education, for example, and they're given some assessment that is measuring that taps into some latent construct of interest. This could be personality, it could be things like depression or student achievement and educational assessments. And based on these responses from this assessment, we then want to we apply some sort of psychometric model or some sort of psychometric paradigm here to try to then get some estimate about the person with respect to that latent construct that we're interested in. Now, in education, for example, a very common or very common example that we see in education, for example, is the PISA assessments, which we use an IRT model to estimate student achievement. PISA does a little bit more than that. But generally speaking, we can use how the student is responding, their responses on like a PISA science assessment, for instance, to try to estimate student achievement. In psychology, we might use assessments that are designed as screeners. And these screeners are, for example, a screener for depression. And our goal is to try to estimate a patient's severity with respect to depression. And here we might use factor analysis or atom response theory as the psychometric model that we use to estimate severity. Now, this traditional assessment paradigm here typically is operated within what's called like a fixed length assessment. And the idea is that we develop an assessment or a scale, and the items on that assessment are fixed. So every individual in the sample or in the population that we're interested in receives the same form of the assessment, generally speaking. Now, there are some drawbacks to that approach, and these were some of the issues that I was interested in this particular project and presentation. But some drawbacks of fixed length assessments in educational testing, for instance, we might be interested in item security or exposure rates. This is like a very big deal in large scale testing, right? Making sure that item security is like a top priority. Depending on the length of the scale, issues around fatigue might be a concern. If the scale is too long, we might end up with responses towards the end of the assessment that aren't of the best quality because of the individual's fatigued. And generally speaking, every person responds to every item, regardless of their underlying levels of the latent trait or the latent construct that we're interested in. Now, an alternative to this approach is what's called the adaptive assessment paradigm. And in adaptive assessment, the goal is to try to adaptively learn an individual's location on a continuous latent space in real time as they interact and provide responses to different stimuli. In this context, specifically items on an assessment. Now, because items are administered adaptively using some sort of adaptive rule or some sort of adaptive algorithms, we can use those responses in a more targeted manner to then produce assessments that are both shorter in length, so the assessment length is reduced, but also we increase measurement precision because the assessment is being targeted towards the individual and how they're responding to the assessment. So it's more of a targeted assessment. In educational assessments, we have an adaptive approach is very convenient and very attractive because it provides better item control, which leads to enhanced test security, and perhaps more from a psychometric perspective, doing this adaptive paradigm here, we can have comparable or even better measurement precision compared to a fixed length assessment in terms of, for example, standard errors. So we can have better measurement precision of the individuals. And because we're reducing the length of the assessment, we might also have a reduction of fatigue in long assessments. And so the big question that I was interested in this project, and I'll motivate this a bit in a couple slides here, is it's really well known how we build adaptive assessments that feature dichotomous or polytomously scored items. So these might be true correct response items or items that are on a discrete rating scale, like a Likert scale, for example. But I was really particularly interested here in how we build adaptive assessments when the items feature a continuous rating scale. But before answering this question, I want to first talk a little briefly about how items are picked within an adaptive environment, right? That's sort of like one of the key features of an adaptive environment is that we administer items in a targeted manner. And so the idea is, how do we do that? What's the process for item selection? Now, there's tons in the literature, there's tons and tons of different techniques that we can use for item selection. Some very popular rules or some methods include the Kohlbach-Leibler information criteria, which is looking at the sort of an asymmetric difference between two probability distributions. Uri's rule, which is looking at selecting items based on their level of difficulty relative to our current estimate of the latent trait. Progressive method, when item exposure needs to be controlled for example. So there's tons and tons of methods, but the method that's perhaps the most popular and the one that I'll be focusing on in this particular presentation is the maximum Fisher information item selection method. Now, the item Fisher information selection method, I'll describe it here for a dichotomously scored item. So we'll first consider a binary item that's either scored true, false, or correct, incorrect, or endorse, not endorse. And so if we have a 2PL model or 2PL IRT model for dichotomously scored items, we'll start off by just showing you the item response function for a binary scored item. So we're interested in the probability of a correct response or an item endorsement, conditional on the person's level of their latent trait or the ability value. And then we model it as a function of using this logistic function. Now, what you can show is using some calculus and some different mathematical techniques is that you can derive the item information function based on a 2PL model or based on the likelihood of a 2PL model. And what you can show is that the item information under a 2PL model is given by this equation here, which is alpha squared, alpha here being a discrimination parameter. This tells us how strong the relationship between the latent trait and the item is. And it's also a function of the conditional probabilities themselves, so the conditional item response probabilities. And so what these information functions look like is like this, for example. Here's an example of a few item information curves for dichotomously scored response data. Now, the way we look at this graph and the way to interpret this graph is that it's telling us for every item here is represented by a different colored curve. Every item has an associated item information. And importantly, this item information here ranges across the values of the latent trait. So within an adaptive assessment, using this item information procedure, we might initialize a person at some preliminary value of theta. Let's say theta equals to 0. We initialize the individual. So here we might initialize a person to be at the middle of this response ability distribution. And we compute the item information at that level of their theta. And we select the item that maximizes item information at that level of the latent trait. So in this example, if we initialize a person, for example, at theta equals 0, we see that the item that maximizes information is going to be this green item. So then using this item information procedure, we would administer the green item to the individual. That's the item that they receive. Now, once that item has been administered and we get a response back, they respond to the item. We use that information to then update our estimate of the person's ability estimate, and then we repeat the process. So then from that new estimate that we currently have, we compute the information function of the remaining items, and we select the item that maximizes information. We administer that item, and the person gives a response, and then we keep going through this process until one of two things happens, generally speaking. Either all items have been administered, so the item pool has been exhausted, or we terminate the algorithm if an acceptable termination criteria has been reached. So we might say, we'll terminate the algorithm if we have an acceptable level of standard error, for example. Now that example on the previous slide was for dichotomous data, or data that were correct or incorrect, or true false. In this context, and I'll provide context about the specific data that I'm working with on the next slide, we're working with continuous response formats. So here I have a really nice illustration from a paper that does a really great job at talking about continuous rating scales, a survey of continuous rating scales in the literature. And these continuous rating scales have a couple different properties from a categorical response scale. For example, something you might see on the top of the screen here, where we have a discrete rating scale. In a discrete rating scale, the individual has, in this example, they have 6 options to choose from. This is an example of measuring pain levels. And so this is typically the sort of examples that we see in like Likert scales, for example, where people are asked to endorse their level of agreement with some kind of items. And we have a really good understanding of how to build adaptive assessments when we have items that have this form here, these categorical response structure. In this study, we were looking at scales that have a response format that looks more like this, the one in the red box. Now, what you notice about this response format here is that it has two anchor points. In this example, the example is pain, no pain, and worst pain possible. And a feature of this continuous response format is that the individual can select the response anywhere along this continuum. So they're not necessarily restricted to just talking or to just selecting one of the predefined endpoints. And so this is the response formats that I'll be considering throughout the remainder of this presentation. But I want to give you some context about what informed this analysis, or what formed the study that I'm presenting on. Sort of give you some background about some of the motivations here. So the data that we're working with that motivated a lot of the ideas in this project here comes from data that we have from the self-determination inventory. The self-determination inventory is an assessment that was derived from causal agency theory. And the main construct here of interest is self-determination, which is defined by Sjogren et al. As a dispositional characteristic manifested as acting as a causal agent in one's life. So it's how this idea of self-determination of individuals. And specifically, this assessment was used for adolescents and young adults. Now, this assessment here has 21 items that is measured on a slider scale or a continuous response scale, like the one I just showed on the previous slide, with two anchor points, agree and disagree. So if I go back one slide, we have disagree on the left endpoint here, and we have agree on the right endpoint. And the individual is allowed on a computer to put any response between 0 to 100. That's sort of the coding scheme here for these response formats. Now, the data that I'll be analyzing and presenting here comes from a sample of 739 students who participated in providing responses to the SDI as part of a larger study. So this is going to be sort of the context and the data that I'll be using to inform a lot of the different analyses that I'll be reporting on. And a feature here is that this scale was originally developed and analyzed using factor analysis. And I'll come back to that point in just a minute here. But a reasonable question you might be asking yourself is, why try to turn this assessment into an adaptive assessment? Well, one of the reasons is that this assessment is actually given to students with various types of, or to children with various types of disabilities, including learning disabilities, intellectual disabilities, autism, emotional disturbance, and so on. And so when we were having conversations, my research group and I, we were having conversations about how we can reduce respondent cognitive fatigue, respondent burden, and trying to improve measurement precision using fewer items, specifically, for example, for that type of population. So sort of we were having these conversations that perhaps a 21 item scale might be too long, or maybe the response format here might be a little difficult for the person, for the child to use. So we were having sort of these conversations about how can we make this a bit more adaptive, a bit more targeted, so that we can reduce some of these features. And so, and going through this, looking at this data here, and recognizing that it was developed under a factor analytic framework, a reasonable question that I asked myself and my colleagues asked ourselves was, can we build an adaptive assessment using factor analysis? Right? It was developed under factor analysis. Can we use maybe factor analysis to try to build an adaptive assessment for this scale here? Now, a feature is through these conversations that we were having with each other is we had several possibilities, several different ideas, and we wanted to build an adaptive assessment that we didn't want to discretize the scale. We figured that would be too difficult to do, and we didn't have a really good way of finding out how to discretize the scale. So then implement it with like a polytomous adaptive assessment, for example. So we wanted to not do anything to the structure of the data itself. And again, just as a reminder here, in this response format, the person can give a response anywhere along this continuum. And so our first approach was, okay, let's try factor analysis. What happens if we try to use factor analysis to try to build an adaptive assessment here? Well, it turns out that under a factor analytic framework, the information function is actually flat. And so in essence, what that means is that you'll notice the equation on the slide here, the information function for factor analysis, is actually not a function of the latent trait itself. You notice the right-hand side, there's no theta here on the right-hand side. In fact, the information function is a ratio between the squared factor loading, that's the lambda parameter here, to the residual variance, which is the side parameter here. So what this means for us is that an item is equally informative no matter where on that latent continuum a person happens to be. And so here on the right-hand side of the screen, I have an example of a hypothetical item information curve under this model, under a factor analytic model. So you notice here, the reason we call it a flat information function is because this item has the exact same amount of information at every single level of the latent trait. And so this is really not ideal for building adaptive assessments. And to sort of illustrate this with the SDI data that we're looking at, here are what the item information curves look like under a factor analytic framework. So here we have the 21 item information curves. And what you'll notice is item 20, for instance, is the most informative item out of the set of 21 items. But not only is it the most informative item, it's uniformly the most informative item. So there's no other item that provides more information at any level or any value of the latent trait. This is followed by item 12, followed by item 21, and then we have the final item here with the lowest information, which was item 3. Now, if we were to try to use this to build an adaptive assessment, essentially what we've done is we've created a fixed length assessment that has been rank ordered by item information. This is probably not an ideal design either, because it probably isn't the best practice to put your best items up first and then have your lowest information functions, your items with the least information towards the end. So really, it's difficult to build an adaptive assessment using the factor analytic framework under this maximum information approach, right? Because every individual would get the exact same form, essentially. Right? They'd get item 20, followed by item 12, and so on. So then that sort of brought us to a halt a bit and said, okay, maybe factor analysis here isn't a reasonable contender for building an adaptive test for that features that I just mentioned. And so I'm going back to the drawing board and trying to think about, what are some of our goals? What are some of the features that we'd like to have from a model for this type of data? And so the final goal was to develop a psychometric model that had a couple key features. First, it was ideal if it featured a non-constant information function. So if it was possible to have information functions that were not flat, so that we could use those in item selection. The model should have, another condition was that the model should have been for continuous response data, so no categorical responses. But we also wanted to respect the bounds of the data, right? We recognized that in a response format like this, there's no other response points outside of this. We wanted to keep all of our information contained within the response range. So we wanted to respect the bounds of our data. We also wanted to account for the skewness in the response distribution that we saw. I showed a slide. I showed an example a few slides back of the distribution of the response distributions of the SDI data. So here are the 21 items and their response distribution. And the final condition was that we would like to be able to put this within an adaptive testing framework. Right, that's sort of the big overarching goal of this project here. And so this culminated in what I'm calling here the beta-Bernoulli mixture IFA model. And so I'd like to talk about building towards this model here in the next set of slides. So this model here, this BBM IFA model, is partially based on the beta distribution. Now, I think perhaps if you're not familiar with the beta distribution, its density function is given by this equation here on the center of the screen. Now, the main idea behind the beta distribution is that it satisfies a lot of the features that we were interested in that I mentioned in the previous slide. And I do want to note here that the use of the beta distribution is not new in the psychometric literature. There's actually quite a bit of literature that has used the beta distribution within a psychometric context. And here, this distribution is indexed by two shape parameters, alpha and beta. This controls the shape of the distribution and what it looks like. And so, in looking at the literature, actually, it seems that papers that use this beta distribution as sort of the foundation of for a psychometric model parameterize the shape parameters. So they parameterize the alpha and beta parameters as a function of some latent trait or some ability or theta here. Now, it wasn't very intuitive to me how we can interpret modeling a shape parameter as a function of theta. So here I'm proposing a different, an alternative parameterization to the beta distribution, here called the mean precision beta distribution. So it's essentially a linear transformation of the shape parameters. Here are the linear transformations I put up on the slide for you. And if we apply these linear transformations, then we have an alternative representation of the beta distribution. Now, this representation here is known as the mean precision parameterization. The mean portion comes from the fact that this parameter mu is actually the expected or the mean. That's the expectation of the random variable that's beta distributed. But it's the expected response. And so that was, I think that interpretation there is very, it's very clean and I think provides a nice way of thinking about these parameters. And then the second parameter here is parameter phi, which is called the precision parameter because it is inversely related to the variance. Now, again, why the beta distribution here? Well, it's because it satisfied a lot of the three out of the conditions that we were looking for. It's for continuous response data. The beta distribution respects the bounds of your data, and it also can account for skewness in the response distribution. Here on the left-hand side, I have different examples of the different shapes the beta distribution can take on, depending on different values of mu and phi. Now, an interesting thing we found when looking at our data was we noticed this interesting behavior in which there was a non-trivial proportion of students who consistently provided responses on the extremes of the response continuum. So these were responses that were either exactly 0 or exactly 1. Now, the literature on inflated responses tells us that we should be modeling those types of responses separately in the situation in which it might represent a different response process. So that was something that we wanted an additional sort of feature afterwards that we were thinking about. There are some papers out there that suggest shrinking the scale by transforming them so that they're not exactly 0 or 1. But usually those are methods that are not advised to use. So then our solution to taking into account these extreme, what I'm calling inflated points, was to modify the beta distribution to a 0-1 inflated beta distribution. And so here the modification is essentially we're tacking on the component that takes into account the overinflation at the boundary points. So these extreme 0, 1 points. Exactly. So here I have a few examples of what those inflated responses might look like in this in a beta model here. So this is what's called the 0, 1 inflated beta distribution. Now the 0, 1 inflated beta distribution is a mixture between a beta distribution and a Bernoulli distribution. And so this allows us to take into account two potential response processes. The first one is what I'll call the continuous component. This is going to be the responses that are within the boundaries that are not exactly 0 or 1. And the second component is the Bernoulli component, which is modeling, going to be used to model responses that are exactly at the endpoints. We have one component that's for the left endpoint, so a response of exactly equal to 0. And we have a component for the right boundary point, or values that are exactly equal to 1. And then two additional parameters here is a zeta parameter, which is a within item mixture that represents the probability of a discrete response. And our second term here is the gamma term, which is going to represent the conditional probability that the response is 1, given that it comes from a discrete response. The way we build the measurement models for these different components is by assuming that the latent trait influences response behavior through these conditional probability parameters, or these conditional expectation parameters. So for the discrete component, so responses that are either exactly 0 or exactly 1, we have a discrete submodel, quote unquote, that we're modeling as very similar to a 2PL IRT model, here represented in slope-intercept form. So we assume that the probability that an individual selects the right endpoint, given that they chose one of the endpoints, is going to be given by this logistic function here. And a very similar process for the continuous component. Now, because the mean parameter here is defined as the conditional expectation, and that's also bounded between 0 and 1. So we use a very similar logistic function here, where we assume that for the continuous component, the latent trait is influencing response behavior through this item response logistic function. Now, one of the key features here of this model is that if you go through the work of deriving the information function, you actually end up with this very fun-looking equation here. Now, the important piece of this equation here, of this item information function, is that it depends on, it's a function of the latent trait. It's a function of theta through these conditional expectation parameters. Right, so it satisfies that other criteria that we were looking for, and that we would have non-constant information functions. And so in principle, then, this should allow us to make it possible to build adaptive assessments for this type of response type. So here on the right is an example of what an item information function for a single item looks like. So it's actually made up of a sum of two components. The first component is the discrete component, the information function for the discrete component. And the blue portion here is the portion coming from the continuous component. And so if we add these up, we end up with the item information function, which is in green here. And so you notice it's not a flat function. Here we see that this item is most informative for latent trait values at around -1. So I want to present a series of simulation studies that I conducted to examine the properties of the model across different scenarios. In particular, I had 3 simulation studies here. I think for the sake of time, I'll jump to simulation study 2, but if you have time, I'll come back to simulation study 1. Just to give you an overview, simulation 1 looked at how the model performs in a fixed length situation. Sort of the idea was, if we can't accurately recover model parameters in a fixed length assessment, it's maybe not a great idea to try to put that in an adaptive framework, right? So we wanted to get sort of an ideal fixed length assessment first before trying to move on to the adaptive assessment. Simulation study 2 dealt with the idea of building an adaptive test. using an ideal item bank. And finally, the final empirical analysis, or the simulation study 3, used the calibrated SDI data and the model here to then retroactively create an adaptive version of the SDI. But just for the sake of time here, I'll move to simulation study 2, since that's sort of what the main interest is here in this presentation. In this simulation, we were really interested in, can this model, this BBM-IFA model, be used to create adaptive assessments? In other words, stated differently, is how well can we recover a person's true theta value if items are administered adaptively? And so here the design here in order to answer this question is our simulation design. I developed an item pool consisting of 50 items. These were fixed across assessments. And I simulated the item parameters. And in this simulation here, it was assumed that the item parameters were known. And so there was no estimation error there was no sampling variability with respect to the parameter estimates. We used the true known values. So this is what I call an ideal CAT scenario. We looked at 2 different item conditions, low and high. And then these were created using by looking at the literature on what constituted a low quality item and a high quality item, and trying to take some of those ideas into account here. And for this analysis, we looked at 21 theta values ranging from -2 to 2 in increments of 0.02. Sorry. Where am I? Okay. So we looked at 21 theta values ranging from -2 to 2 in increments of 0.2. And so for every theta value, we simulated 1,000 respondents to reduce sampling variability at each value of theta here. Now in this simulation here, all respondents were initialized at theta equals 0. And there were 2 item selection procedures that we implemented. The first one was maximum information, using that equation that I showed on the previous a couple slides back. And the item random selection procedure, which is essentially picking an item at random. So this was sort of used as the baseline. And so the way the simulation process works is for every value, for every theta value, we initialize the individual at a theta of 0, regardless of their true theta value. We initialize them at theta equals 0. We calculate item information and select the item that maximizes information at that value of the provisional estimate of the latent ability. We simulate a response for the selected item, and we update theta using that newly available response. And here we used a Bayesian adaptive framework for all of these analyses. And so here we look at the posterior standard deviation of the most recent estimate. If that standard deviation was below 0.3, then we terminated the algorithm and kept that estimate as the final estimate. Otherwise, we repeated this process starting from step 3. So we discarded the item and then picked the next most informative item to administer. Now, going into some of the results, here we have results with respect to the average test length for the BBM-IFA model for items that were administered using maximum information or the item selection procedure. Here we have item low and high item qualities. And we'll see that in green here, in the green, we have the average number of items that were required at every level of the latent trait. Now, if we look at the low item quality condition first, we see that it took an average of around 10 items for us to reach that the acceptable threshold that we had set of that posterior standard deviation, around 10 items. Whereas using a random item selection procedure required around 17 to 18 items on average. And that was consistent across values of the latent trait. Moving over to high quality items, we actually needed about 5 items in order to achieve our specified measurement precision here. And oops. In low item quality, with respect to the random selection, we needed about double, almost twice as many items. Here it's still not a large number, but we're seeing that in these high item quality conditions, this represents a reduction of up to 77% of the items. In low quality items, this represents a 41% reduction in the assessment. Now, an interesting feature that I wanted to present here, and something that's been sort of baffling me for a bit, is when we looked at the bias results, the bias of our estimation, we noticed that we sort of have this really interesting pattern in which it looks like at the lower end of the ability distribution, we have a slight upward bias where we're slightly overestimating the trait. And at the upper end of the ability distribution, we sort of have a downward bias. We're sort of underestimating our effect here. And we saw this for both low and high item quality conditions. So this is actually something that I'm currently looking at a bit more in more detail to try to get a better sense of what's going on here. One thing I do want to mention is that the plots here look very similar across low and high item quality conditions. But the reminder here is that the results were taken after the algorithm terminated. And so even though we have similar performance, the high item quality conditions here required less items to have sort of the same behavior here. And so what I think is going on in this graph is there might be what's called an attenuation paradox, which is something that Vander Linden and Glass mentioned in their book, which says that when you're using maximum information, there's sort of this really interesting thing where the best item is actually not the one that's closest or the one that maximizes the item information. It was something that was also mentioned by Lord and Novick in their classic book. And so they call this the attenuation paradox. And I have a suspicion that perhaps that's something that's going on here, but it's something that I'm looking at a bit more closely. In terms of the proportion of the posterior, the 95% credible intervals that contain the true ability estimates, we see that we have pretty good pretty good coverage in terms of credible intervals, both for the low item qualities and the high item quality conditions. Now, I want to jump to the final simulation study, which was where we use the actual SDI data to build the adaptive assessment. Now, one thing I want to note here was that the SDI, the data that we have, was administered as a fixed length assessment. So the analyses that I'll present now are more of this hybrid, what I'm calling a retroactive analysis. So it's this idea of what if this assessment was administered within an adaptive framework, since the actual responses themselves were administered using the entire 21 items that we have. So this simulation study proceeded in 2 steps. The first step was to calibrate the item parameters for the SCI using the BBM IFA model. Here we used Hamiltonian, Monte Carlo, and Stan using specifications that were essentially non-informative priors across all of the model parameters to try to minimize the influence of the priors here. And we used the posterior means in step 2. So once we got the posterior distributions of the item parameters, we use the means in step 2. And step 2 is where we create that adaptive assessment. And here we follow the same procedure that I mentioned in the second simulation study, where we administer the item, we simulate a response, and then we update our estimate of the person's ability as they progress through the assessments. So the same design, but the thing here is to note is that the item pool now only consists of 21 items. 21 items that we had access to at this time. Here are the information curves. Both the item information curves are on the left-hand side here for every item within calculated using the BBM IFA information function. And if you add these up, you actually get the test information function or the test information curve. And so this tells us at what points of the latent trait, at what values of the latent trait distribution this test is most informative. Now you'll notice this, according to this graph here, this assessment is most informative for individuals who are below, who are quite below on the latent trait distribution. If we get to about a theta of 0 and beyond, we really don't have a lot of information from this assessment. So it seems to only really be informative for those on the lower end of the self-determination trait. Now going a bit more into the breakdown of the responses of the SDI, I mentioned earlier that there were a non-trivial number of students who were consistently endorsing those extreme endpoints, right? So here we see about almost an average about 25% of students were consistently endorsing those extreme endpoints for a given item. Looking at that further, we noticed that most of them are actually choosing the right endpoint the most. So they were sliding the bar all the way to the very end, overwhelmingly so. And very few were using the left portion of the, responding with the left extreme of this response category. Now, after applying this adaptive assessment using a similar procedure to the second simulation study, we get this curve, which I think is really the meat of this project here, which is telling us the average test length for this SDI item, for this SDI assessment. And we'll notice we have this really interesting nonlinear trend here where at the lower end of the scales, which is what we saw in terms of the item information functions, we can actually reduce the assessment up to about 14 items using maximum information, and about 17 items or so using 18 items using the random information, the random item selection procedure. And you notice that the number of items that's required actually goes up as the ability trait increases. So after at about a theta of 0 and beyond, we actually exhausted all of all 21 items. So what you're seeing here is this is the us exhausting all 21 items. So all 21 items were administered and we still weren't able to, the algorithm terminated. So we didn't reach the posterior that we were, the posterior cutoff that we used to terminate the algorithm. But there's some evidence here that at the lower end of the traits, we can reduce the assessment to some degree. So if using the, compared to the fixed length assessment, we use this adaptive approach for individuals who are lower on the trait here. We can reduce the item by the assessment by up to 33%, which I think is somewhat considerable in some sense. And then here I have some additional results looking at the posterior credible intervals. We have very similar findings to what we had in the second simulation study. And the posterior standard deviations. We'll notice that again at the lower end, we seem to have lower standard errors or standard deviations, posterior standard deviations, but increases as we get towards the upper end because there's not a lot of information at the average and above of this latent trait continuum. So this retroactive analysis here at least gives some preliminary indication that it is possible to take these item types, put them within an adaptive assessment, and produce adaptive assessments that are quite shorter in length. And of course, there's that caveat of it being towards the lower end of the scale. But in those situations, we saw a reduction of 33% of the assessment length. Now, there's a lot of caveats and there's sort of a lot of limitations here that I think are important to mention. First, we only had 21 items to work with to build an item pool. That's very likely way too small to build a reasonable item pool. So in the future, we're looking towards using a larger set of items that weren't available for this analysis to try to build that up a bit more. Some other limitations from this particular analysis was that I think it's important to remember that the STI was not developed with the intention of being put within an adaptive assessment framework. That was sort of the conversations that we had afterwards once uh, we noticed that the types of individuals that were these assessments were given to. And so that's right. The STI itself was not designed to be put within an adaptive assessment. Generally speaking, that would ideally that would be a step that um, would be thought about first, right? We have an item pool. We know we want to build an adaptive assessment. Now let's go ahead and build that. But here we sort of work backwards. We said, we have the scale already. It's 21 items. Let's try to build an adaptive assessment. So it's sort of this retroactive approach, which in some sense is a little less than ideal. But I think given some of the results that we saw here, I think there is some preliminary results or some preliminary evidence that this is a promising area for future research, and it's something that I'm looking forward to continuing to expand upon. And I've been thinking a lot about some other applications of this, and I think some applications include applying them to pain measures or to PROMIS measures, depending on the type of response scales that they use in those types of assessments. But I'll conclude here by saying that one of the main contributions here was that derivation of that non-constant information function, and then showing that, at least preliminarily, it looks like this seems like a feasible or a reasonable sort of attempt at trying to build an adaptive assessment with these continuous response formats. I like to think of this study as a pilot study, right? There's a lot of interesting ideas here. I think in this analysis, we're looking at a lot of different moving pieces, but I know there's lots of work that needs to be done to sort of refine the technique and the ideas that I presented here today. And I would like to wrap up by acknowledging my colleagues, Jonathan Templing, Kerry Sjogren, Tyler Hicks, Jesse Pace, and Katie Mintz, who were provided so much support and really valuable guidance through this project. And thank you very all. Thank you all very much for your time. Before I turn it over for questions, again, I'd like to thank Clint, Daphne, Susanna, and the rest of the PRISM group for hosting such a great seminar series and for inviting me. It's a pleasure to share some of this work that I've been starting off with you all. And if you'd like to reach out to me afterwards and like to chat more, my email is up here on the screen. So thank you all.
Thank you so much, Dr. Martinez. We had one question in the chat from Dima that I think is a great one to kick us off with. So Dima, if you want to unmute and ask.
Hi, good evening. Thank you, Dr. Martinez, and thank you everyone for this. This is really interested, and I like how you summarize actually one of the major, how can I say it, challenges I face when I analyze something with not. I was thinking about this, that you can analyze the items that have a lot of how I say it, subjectivity related to the personal opinion. And I'm working on some educational assessment for language, and the first thing came to my mind is the writing rubrics. For example, I have this model of writing a score out of 10 skills. So each skills have set of another 4 breakdown judgment under those skills. So I have this rubric of 4 scores, and I did this multi-grading multiple IRT analysis, but each time I try to run it, it always gives me those weird values sometimes for some of those skills. I didn't try it, but I tried. The next step for me was to break down those 10 skills to the smaller component and see what's happened. But when I saw your model, I think I can use the other way around, where I can put it in a scale of 4 rather than break them down. So what do you think?
Yeah, and that was sort of some of that. That's a great question. And those were actually, a bulk of this project was thinking about, should we do that? Should we break it down and discretize it, right? That has benefits in some sense, that you simplify the problem and that you're going from a continuous format to a discrete format. And in some sense, we can think of that as sort of a simplification. but it sort of also brings up these questions of where do we make those cuts? What are sort of the guidelines that we use to inform those? And we really didn't feel that we had a good sort of position to make those statements. It was mostly arbitrary. And so, yeah, those were the ideas that sort of led us to think, okay, let's respect the nature of the response and try to find a model that will do that instead of us trying to force our data to fit some sort of mold, model that already exists.
May I have a follow-up question, please? Do
Yes.
I need, before running this, do I need to have kind of consent across all rater, kind of inter-rater validity or something on those score that I'm going to use, or it is okay to just run whatever I have from the information without checking to do such, to use this model?
Yeah, you cut off at the very end of there. Can you repeat that last portion, if you don't mind?
I mean, do I need to have kind of consent or agreement from the rater on the rating scale and use
I
those value with the agreement on that model, or can I just drop all the information with that model and try what's coming out?
You could probably use the radar information function in it. I That's a great question. I think I'd have to think about this a bit more, specifically in sort of how those rating aligns with the. It's a great question. I suspect
Yeah,
you
I'm
might
sorry,
be
I
able to
dropped you
do.
with so many surprises today. I'm sorry.
Yeah,
I
no,
know.
those are great questions though, because I think these are related in some sense. Yeah,
Yeah, thank you.
but yes, I'm happy to continue chatting. I know I probably didn't answer the question to your satisfaction.
I will try to generate a simple model and send it to you if you don't mind.
Sure, that would be great. Yeah,
Thank you.
yes,
We're
yeah. Thank you.
almost at time, but we have one question from Jay that I think is a perfect one to send us off and might be super short. So, Jay, do you want to unmute and ask real quick?
Yeah, sure. One of the things that I've noticed about this, I haven't worked in this area in a while, um, and it, um, is there's a lot of options now, almost too many, which is to say to deal with things like the zero inflation and boundary points and all that kind of stuff. So, because there's hurdle models,
Mhm.
there's a bunch of different options, and I'm sure you talk about that in your paper, but one in particular that your approach reminded me of. Uh, by the by, I wrote one of the early papers, a couple of early papers in this area, but there's been a lot of different sellers, sort of somewhat independent research going on, and people aren't
Mhm.
necessarily communicating. Um, but one of them is somebody I think who was actually at NYU, a guy named Kubinak or something. I'm not exactly sure how. I don't forget his first name, but he wrote a model called ordered beta regression, and
Oh,
I have a very strong suspicion that your Bernoulli mixture and ordered beta regression end up being if not identical, extraordinarily similar.
mhm.
Um, welcome to this field. There's an enormous amount of reinvention because people are sort of working in different areas, and then all of a
Mhm.
sudden, yeah. But I'm happy to see some the adaptive thing because you're right. Gaussian factor analysis has a flat information function, so
Mhm.
it doesn't make for an adaptive of test. And I know when I first started working this, we pondered some of these kinds of things, but either due to the lack of data or computational limitations at the time, it
Yeah.
it wasn't happening. So it's interesting to see more developments. As I said, I've only recently started to venture my way back in it. But yeah, have a look at the
Mhm.
Cubinet or Cubinetch. I
Yeah.
don't know how he says his name, but have a look at that because I have a feeling that it's either the same or it's like, you know, very similar. So take
Mhm. Mhm.
take a look. Anyway, we should talk some more when we get the chance.
Yeah, that would be great. Yeah, and I'll definitely take a look at for that. Was it the ordered beta?
No, just
Ordered
send me
beta?
an email. I'll send you the link. All
Okay, sounds good. I will do that.
right. Catch you
Yeah,
later.
thank you. Yes.
You're welcome.
Have a good one.
Bye.
Aw- Awesome. Well, I want to thank everyone so much for coming. Our next PRISM seminar is going to be on, let me check again, very early March. So it's going to be March 5th. So hopefully I can see most of you there. So thank you all, and join me in thanking Alfonso again for coming.